Now we want to get into actually drawing Lewis structures. And we're going to talk about a method or kind of a formula you can use to come up with Lewis structures for molecules that's a little more kind of a process as opposed to what we've talked about so far. And so what we want to focus in on is ways to deal with more complicated molecules. So far, we've drawn Lewis structures by drawing out symbols, looking for unpaired electrons and adding them together. And that works, and you can always do that. But sometimes some more fringe cases will be harder to see, and it's just going to get tedious to draw out. So we want to come up with overall better approaches that are more generalizable, a bit more algorithmic for creating Lewis structures. So what we're going to particularly focus on are binary covalent compounds. These are things composed of two types of atoms. And specifically, we're only going to have one of our first type of atom. So you can see at the bottom, AX3, this is A, would be the atom in the middle, bonded to 3 atoms of atom type X. So one of the important things that this may seem, even though this says we're only going to learn how to draw Lewis structures for this type of molecule, this is actually most molecules. Most molecules, most small inorganic molecules follow this type of pattern. Rings and complicated chains aren't that common in molecules. So it's generally going to be A in the middle with N outer atoms. And we're going to learn how to draw these Lewis structures, which is going to get you through most Lewis structures of most molecules. Okay, so overall, we want to have an algorithmic approach here. So the first idea is always determine the total number of valence electrons in the molecule. That just means count, use the periodic table to figure out how many electrons each atom has, and then, add up how many you have in the molecule, put those all together. You do need to characterize if it's a cation or anion based on charge. Step 2 is bond all outer atoms to the central atom using single bonds. Step 3, add the remaining electrons as lone pairs, starting with the outer atoms. If the electrons remain after the outer atom has octets, add those to the central atom as lone pairs. The central atom, well, these are real long. So let's, take a step. Let's go through this piece by piece, look at an example, and we're going to follow this process. We don't need to memorize this all right now. Let's go ahead and look at an example. PCl3. The one important part that we did walk through was getting that total number of valence electrons. This is always the most important step for determining a Lewis structure. Like we said before, if that Lewis structure doesn't have the right number of valence electrons, it's wrong, right? You haven't accounted for where everything goes because you don't have the right number of electrons. You can't have the right bonding pattern. So I have 1 phosphorus, that's 5 valence electrons. I have 3 chlorines. Each one brings in 7 valence electrons for a total of 26 valence electrons. Okay, so now I know right away that at the end of the day, I better use 26 valence electrons. So I want to bond all outer atoms to the central atom using single bonds. Well, what is the central atom? Well, we know that based on how we write these structures, there's a reason we write molecular formulas in the way that we do. The first atom is the central atom. So whatever the first atom that's written is the central atom. The other atoms are going to be the outer atoms. So my basic formula is going to be P in the middle, single bonded to 3 chlorine atoms. I don't use double bonds or anything like that. I just put those on. I may need to use double bonds, and we'll come back to those. But basically we can think of, I'm just making a base skeleton to just connect all my atoms. I don't make loops. I don't connect my outer atoms. I don't do anything like that. I want to just keep the central atom, and it has bonds kind of like spokes in a wheel sticking out to all the outer atoms. So now what I want to do is I want to add more electrons as lone pairs, starting with the outer atom. So I want to add some lone pairs, and what I want to do is I want to figure out how many electrons do those outer atoms need until they hit an octet, until they end up with 8 total electrons. So the first thing is I got to figure out, well, how many electrons do I have left, right? We said this was an accounting practice. I started with 26 total. In starting to draw my Lewis structure by implementing single bonds, I have already assigned 6 electrons. There, right? I have 3 bonds. 3 times 2 is 6 total electrons. So I now have 20 electrons left to fill the octets of all my atoms. My outer atoms of chlorine each have 1 bond. That is 2 electrons. They all need 6 more, which means they will need 3 lone pairs. That's true of all of these chlorine atoms. Right? I add enough lone pairs to give each outer atom an octet, right? Fill them up. And if I'm using single bonds, it's always going to be 6 here. Okay, so we assigned those as lone pairs. Now, if electrons remain after the outer atoms have octets, add those to the central atom as lone pairs. Okay, well, I got to see how much do I have left. Well, if I can just count electrons in those outer atoms lone pairs and count the dots, and that's going to give me 18. That comes from the fact that I added 6 to each outer atom, and there was 3 of them, so 18 total electrons in those outer atom lone pairs. If I do 20 minus 18, there are 2 electrons left. So those 2 electrons have to be assigned somewhere, and what I can do is basically use them to fill the octet of the central atom. In this case, the phosphorus. That P needs 2 more electrons. And once I add those 2 more electrons to the phosphorus, it also has an octet. So what I can see is by figuring out accounting-wise how many electrons I started with and how many I was assigning to these different things, lone pairs and bonds, I've gotten to the point where everything has an octet and I have used up all my electrons. So this is the Lewis structure for PCl3. And we can always follow this protocol to get there. You may run into issues like right here. If you were to subtract out those 2 electrons that you used for phosphorus, you got a negative number. That's a sign that you probably had a mistake in this initial calculation up here in terms of figuring out how many total valence electrons. Things are going to want an octet. And so if you kind of are running out of issues, if you get a negative number after you assign those outer atom lone pairs, that's probably a sign that you don't have the right number of total valence electrons that you're working with. So, you never should be ending up with negative numbers here. Participation 625, question 3. Determine the number of valence electrons in one molecule for the listed formulas: H2O, Cl2O7, and Br2. This is the third question on participation 625 due Thursday, June 25th at 11:59 p.m. over on Blackboard. Link to the assignment is right below the links to these videos. Again, determine the number of valence electrons in one molecule for each of the listed formulas. It's water, dichlorine heptoxide, and bromine. Another participation question in this video. Got pretty high rate. Got more videos to go. See you in the next one.